of design for manufacture that we follow in the industry for manufacturing of plastic parts. So since there are not many of us over here today, many people I guess couldn't join because of the timing. So if anyone could tell me anything about why should we learn about plastic defects, what's the reason that we should learn about why are there defects in manufacturing? Please feel free to unmute during the session. After I stop, like I'll take frequent pauses to communicate and chat with you guys. So then you can always unmute yourself and ask me questions if you have any doubts, if you have any inputs. It would be really great. You can also use the chat box if you cannot unmute. That is, yeah. So can someone tell me about why defects is learning about defects in plastic components is actually necessary? Mm. Okay, no one has any idea. Okay, I'll continue then.
Sir, to get
Yeah.
the high accuracy products
Okay,
without
Arjun.
any problem, and for the customer satisfaction, and in the mass production, we need not to check each and every part. So we consider all the particular parameters that will lead to any kind of defect in the plastic products.
Exactly, Arjun. You actually nailed all the 3 points perfectly. So here it is. So this is just a brief on. I'll just start by giving a small revision. Many a times you guys may have not attended previous sessions where I discussed this in detail. Arjun, I guess you were there in the previous one. I remember you communicating back then as well.
Yes, sir.
Yeah. So this is the injection molding machine, right? So in the injection molding machine, you have got various parts that it's like an amalgamation of different components coming together to form this one plastic part. So how does it work? Basically, you have plastic billets or plastic pellets that are really tiny chopped pieces of plastic, which is added into the hopper over here. So after the plastic is added to the hopper, this falls into the screw starts pushing it forward. These rectangular objects that you see over here, right, the orange color ones, these are called as band heaters. So band as such means the wristband or some like a thick round component that surrounds the entire injection of the plastic this mold of the screw, sorry. And what this band heater does is, since it is in the shape of a band, it provides a very even heating. So so as not to burn the plastic part, or not to overheat a particular part while while some other part is running really cold and solidifying on the screw itself. So hence band heaters are applied to ensure that there's uniform heat throughout the entire screw, so the plastic melts evenly. Then after this happens, the screw rotates and starts pushing the plastic towards the front of the injection over here. So after it pushes it to the front of the injection, what happens is, as you'll see in a minute, this screw entire thing moves forward and pushes the molten plastic into the mold. Now, the reason for pushing it and not just letting the screw go is so that we have enough of speed, so that the plastic is injected into the material at a really good speed before it can start solidifying. All the material should be, ideally, all the material should be transferred into the mold. But of course, we do not live in a world where calculations and stuff come into, translate into the real world 100%. We will always have real world conditions. So what are real world conditions? They are basically that the mold is going to be a little cooler. When you start injecting the plastic into your mold, you will have some parts which will be solidifying quicker than the others. But while designing the mold, while designing your plastic part itself, you have to make sure and have that visualization that this does not happen, because that's called as uneven cooling. And there are a lot of problems that come with uneven cooling, and that's exactly what we'll be discussing today. So yes, so basically that's why you have this entire injection pushing the plastic at a really good pressure into the mold. Then this mold, after, like, when you see this closing, right, the closing happens with the help of a clamping mechanism. A clamping mechanism ensures that both the parts of this mold is closed and clamped completely shut without any gaps. And even when there is pressure being applied from the inside, that is when plastic is being sent under a high amount of pressure, this mold shouldn't open up, and that also will lead to another defect. So that also we'll be discussing today. Then at the end, you have these ejector pins that push the component out post cooling. So we are. Does anyone have any doubt in the injection molding part? If anyone has any doubts, please put it in the chat box or unmute yourself, because you really need to understand the injection molding process in extreme detail to understand how different defects work. Guys, any doubts?
No, sir.
Okay. Anyone else, guys, who has not attended the previous session? Arjun, of course, will have his concepts very clear on this one. Anyone else over here, like who has even the slightest bit of doubt about the cooling part of it, or maybe why is pressure required and things like that?
Sir, what about the left part between that transferring that plastic, molten plastic? If
I
this
I
will
didn't
be,
I didn't
pardon,
understand. So one second. Let me go back to the PPT. And okay, so you're talking about this portion. That this is the mold, right?
yeah, yeah, this mold.
Yeah. What happened to that?
If it is solidified before the temperature is down, then what happened? The machine will be stuck. In that case,
No. Okay, so these parts, no, I didn't catch your name, just Abdullah. Okay, so Abdullah, it is how this works is basically these parts are going to be made out of really hard material, really hard metal. So it's not very easy to damage the machine itself. But yes, the part will completely fail. You will have to stop the assembly line, and setting these units up is a task in itself. It takes quite some time to even set, even for the initial testing phase, you need to set these machines up. So if you have uneven cooling and it's not calculated, or the part is not properly designed, you'll have a lot of problem getting that right balance, because everything needs to be in a proper balance out here.
yeah, yeah, got it.
Okay. Any other doubts regarding injection molding? Okay. If you have any, please drop a message in the chat box. I'll get to it as soon as possible. Okay. So yes, now coming to why do we want to study the defects in plastic? So the first one would be improve the quality. Now, as you know, Arjun spoke about it, that we need to improve the quality of the finished product. Of course, today if you go to buy anything outside, you want the best product for the best price. So if you're going to pay 10 rupees and get a bad product, and somewhere else, someone is selling the same product for 8 rupees and with much better finish, of course you'll go for the 8 rupees. Even if the 10 rupees one is branded and things like that, you'll be like, okay, this one looks more attractive. So or maybe not even looks, the entire quality feels better. So that's why you need to ensure that whatever you are aiming for, the price point that you're hitting, your quality needs to match it or surpass it. You cannot always have anytime have a quality below what your price point demands or your competitors in the market. Second is understanding the basics of mold design. So so mold design is a completely different topic. Okay, so I am a plastic component design engineer. So it's not my job or not my responsibility to understand the mold. But if I don't do that, and if I submit a component which cannot be manufactured, if I've not thought about anything, and I send it to the guys who are designing the mold and who are manufacturing the mold, they'll directly send this part back to me, and they'll be like, we cannot manufacture this. Make some changes. I'll be like, okay, what is the changes? Then they'll sit and they'll teach me. Not a very sensible way of working. Maximum, if it even happens, it shouldn't ever happen. But if it even happens, the maximum back and forth that is tolerable is max to max 2 times. Anything more than that is you start losing money for your company, for yourself if it's your own business and things like that. So so you need to understand how these mold functions, the basics of mold. How do you design your component so that when it comes into the real world, because see, in CAD I can literally design an Iron Man armor, right? If you give me the dimensions, if you give me the drawings, an entire Iron Man armor can be made. But when you get it out into the real world, will it function? No, it won't, because the basic principles that makes the Iron Man armor what it is the arc reactor that is there. So people who are Marvel fans will get my reference. It is basically the power unit that is there in the chest. That power unit does not exist in our world, right? So this is what we need to understand. Anything can be done in the virtual world, but when you start getting things into the real world for real world applications, it becomes very very critical to understand that, okay, I need to ensure that everything is manufacturable. Things do not fail. If I'm designing something that has got multiple parts, say there are 10, 20 parts that need to fit into each other, I need to even take into account design for assembly at that point. Because after you have designed and whatever, it went through manufacturing, perfect, you designed it for manufacturing. But when it goes to assembly, if there are 10 parts that are identical, but you don't need to go in specific places, the workers who are working on the assembly line wouldn't be able to do it because they are not the ones who have designed. You as a designer, yes, if they give you the product, they're like, okay, place these parts where they're supposed to go. You will do it quickly because you designed it, but they have not designed it. So that's where design for assembly also comes into place. So that's why we need to understand the basics of mold design, the basics of design in itself, and that's why you need to learn about the defects. Okay, and learn how to properly design a plastic part. So this goes hand in hand basically. Once you understand the basics of mold, you will also understand how to design a part with the proper, tooling direction, the angle at which the mold opens. If you go out there and on YouTube, you'll just search a bit about these molds, how they actually function. You'll see really really complex parts being made at some weird directions. So if I had to give you an example of that, uh, one second. Yeah. So if say this is an automobile bumper, okay. So here we'll have like the headlights, a place for the headlights and things like that. So not necessary that the mold opens in the exact vertical direction for this thing. The mold sometimes, because of complex shapes, could also be opening in this direction, right? Like this and like this. So I don't know how to draw it in the 2D work plane over here, but yes. So how it works is basically, if this is the bumper that I was talking about, right? It is a bit curved. So in our mind, when we look at it and we think about how this could be manufactured, simple thing is, you have the core part out here which opens from here, and then the cavity part opens from here, and here you have your part. uh, it doesn't work like that. Sometimes if there are cutouts at this angle inside the bumper, you can have the mold that, like, your cavity part will open like this, and then the core part will open like this. It can be at an angle as well. So that is called as pulling direction, or in which direction the mold is going to open, or the tooling direction, tooling, tooling direction of designing the part. So that is what we need to understand. Now, the first defect that we are going to talk about is flow lines. So as you can see these lines over here, right? They like form a particular pattern. They all come together over here, and then they split and split and split and split. Why does this happen? So can someone tell me, what do you think could be the reason for this flow line? Now, of course, this is not an aesthetic element. It looks very bad. In fact, this is like the front fender of a cycle or a motorcycle, and it has a gloss finish to it. So when you have this flow lines, it's going to look horrible. Can someone tell me, what do you think? Why does this flow line occur? Anyone? Unmute, put it in the chat box. A random guess. There are no wrong answers over here. Feel free to, tell me what is your opinion on this one.
Because of the material.
Okay, like I didn't understand. Like, just elaborate a bit on that.
Yeah, I think the combination of the metallurgy science, MT.
Okay. So yes, Abdullah, it is not about the materials in this one. Basically, this is a homogeneous material, right? It is the same material throughout. This, what you're saying about this connection point, that is very relevant when we are talking about what do you call composite mold. So composite manufacturing is something similar to the toothbrushes that you see, where you have your toothbrush body made out of plastic, and then you have a rubberized material. So that is a composite this, and that is where you will see a difference. If both are plastics, say one is a harder form and one is a softer form, there you may see some melting and this line occurring, but that is a weld line kind of defect rather than a flow line. So now flow lines is Abdullah, I guess you only wanted to know ki what happens if this material is not cooled properly. As I told you initially, that if cooling does not occur at a particular rate, so that is when these flow lines occur. So how this happens is one second, variation in cooling. Perfect. Soumya Sinha gave the perfect answer. Variation in cooling speed of plastic as it flows in different directions through the mold. Perfect, Soumya. That is the correct answer. I'll just build up on that a little bit. So what you have is basically if this is your mold, okay. So you have plastic that is going to flow through this. Now, since this part, the upper surface and the lower surface of your mold, so the molds are constantly cooled. Okay, for quicker manufacturing, you could have a heated mold as well, which is not applied because of the cost that comes into play. So you will have your plastic that flows into the mold. But what happens is since this part is cooled, you will have a layer form over here, and this layer will start cooling. These two layers will start cooling much, much, much quicker. Now, after this layer starts cooling, what will happen is it'll start attracting more flow material onto this one, and then you'll have then the material starts building, and at the end you will have two different set of materials coming and meeting each other. So that is one of the biggest reasons why this flow line occurs. Secondly is if your injection speed is too slow. So again, that's the same issue. So now Pranay, you've got a lot of background noise, Pranay. Yeah. So now, if you imagine when this part was manufactured, what is the issue? Now the material, of course, and hello, hello. Yeah. So the material, of course, entered in from somewhere over here. Here you had the gate, or here you had the sprue that sent the material in, and then the material started cooling. And then if you notice a pattern, it started from here, this portion. And this is how the flow line started building. So why did that occur? That is because of that hole that was over there. Maybe that material over there started cooling faster. And once this so plastic, once it starts cooling at an uneven rate, it is like a dominoes effect. Like you knock one piece off, and then everything starts tumbling after that. So that is the same case with plastic. So when this material cools at an uneven rate, that's when this constant addition of layers happens, and every time these layers adhere to each other, like first layer one cools, then layer two cools, then layer three cools, that's when you can see this streak like pattern. So this is an undesirable thing, and we do not want it in our plastic component. So how do we change it? First thing would be to use heated molds, or molds that don't cool that rapidly, or don't run the coolant through your molds at an early stage. But what will happen with that is your production speed will reduce. So how do you prevent that? So it is very simple. Yeah, so I'll just explain how this works. Is basically if this is the cavity side of your mold, and this is the core side of your mold. Okay, so here you will have your component being formed. Okay, now generally you have got coolants running through these mold. Now coolants can be either water, it could be water mixed with a certain compound that causes the entire mold to cool down rapidly, thus increasing your rate of production. But that can result in these flow lines and uneven cooling surfaces. So how do you dodge that? Is by adding, if you remember band heaters, something similar to that, which provides even heating. Actually, not even heating. You want something that will keep the plastic warm. When I say warm, you want the plastic to be in something like a semi-solid format, something like a slurry, something like a very, very thick soup kind of thing. You do not want it to be completely molten, whereas you do not want it to solidify. Now, as I told you, if you are going to keep it warm for a certain duration, wait for it to fill up, then you are going to cool it. Of course, you will waste a lot of time when it comes to production, and that would be a loss for the company if this thing is applied when the part that is being manufactured is of really high quality, or maybe it is the most aesthetic part. So here, if you take this, okay, this is like a wireless earphone. Now the only thing that makes this thing look good is how the outer surface is finished, right? Until and unless I open the case and see how the ear pieces are in that, it does not matter to me. When I look at it at first glance, and if I see these flow lines, and if I see some, really unappealing things, of course I wouldn't look at it. So when you're manufacturing something like this outer case, it is a thing of great importance. So over there, yeah. So when you're manufacturing something like this, there you have to make sure that you can waste a little amount of time for getting the right component. Okay. Hello, everyone who has joined recently. So yes, second thing that you can do is increase the amount of injection speed. So basically, when you are injecting, you need to inject it at a much higher speed. It happens really quickly, but even faster, maybe little faster. If that is possible, it would be a much better alternative. And the last alternative is ensure that the plastic is heated enough right at when it is being injected. If the plastic is very close to solidification point at the point of injection, that's when you'll have problems and it will cool much quicker. Yes, even cooling. Yes, Soumya, you do want even cooling, and that's that these are the ways that you can attain even cooling. So I'll just run through it again. You can have heated molds. Second, heated, I mean, the molds kept at a warmer temperature. Second is increase the injection speed. So these will be the two best options to avoid flow lines. Then next we come to flash. So flash is something that people who have attended the previous sessions will know about, and I want you guys to unmute and tell me what happens and why does it happen. Like what is the cause for flash and what flash exactly is.
Flash is the extra material that comes out of our mold
Okay, and why does it come out, Arjun?
due to the either of the mismatch or due to the fast the mold can't resist the pressure.
Okay, correct answers. And how would you say should we counter it?
What, sir?
How will you counter it? What is the solution to avoid flash?
Either reduce the pressure or make sure that there is the gap is very minimal between the molds, like the
Perfect. Perfect. Exactly again what I was looking for. So mold not closed properly, close pressure not sufficient. Soumya, again, even you are on point over here. So yes, so here you have flash, right? So how does flash work over here? Basically, like if you look at this is called as the flash. Now you ideally want this rectangular component, like having straight walls. This is what your component should look like. But if you see over here, you have got this extra pieces that is coming out of it, and this is what you do not want. But and this part is called as flash, something that leaks out of the mold. And flash is a good look at bottle caps. Like nowadays you're getting these PET bottles, not exactly PET bottles, but juices are coming in plastic bottles which are very cheaply manufactured. Then there are a couple of children's toys. That's where you'll see this flash very prevalent. So we are Arjun have raised a very good point about mismatch of molds. Mismatch I'll come little later. Let's consider now both these molds close exactly at exact points. So what happens is, now if the clamping mechanism, the clamping unit that I was telling you, is not strong enough to resist the pressure, that's when you will have this red color material, right? uh, so you'll have this red color material leaking out into these crevices over here. From here it could be, from here it could be, and this is in the 2D plane, but of course in the 3D plane also you could have that amount of leaking because the plastic is being pushed in with a high amount of pressure. And this pressure is very important, because plastic, when it cools down, it shrinks. Ways to avoid shrinkage: one is while designing, you consider which material you're using and you see the coefficient at which it shrinks, and you can add that tolerance while designing the part. This is very what do you say, something that you get by calculation, and it is very unreliable as such. It won't produce quality parts. Second, how you can avoid the shrinkage is by pumping a good amount of plastic and ensuring that there is a good pressure inside the mold so that this warpage doesn't occur. But if you add this amount of pressure, and this is pressure exceeds the limit of the your clamping unit or the clamping device that you're using, of course you'll have plastic leaking out from the sides of your mold. So next, coming to his point, Arjun's point, and that would be mismatch. So mismatch was a very big concern in the past, where people had not nailed how to manufacture molds properly. Today it's not that big of a concern, because the machines have improved, the mechanisms have improved, and also you have something called as guide or locators. So basically, you have locators for your plastic parts. These are completely different. In molds, what you have is, if this is the core side of your mold, for example, you will have like a locator pin out here, which will be tapered to a certain degree, and on the other side as well. These pins are also made out of really hard materials. And if this is the core side of your mold, right? So in the core side, you will have some holes, and this could be varied. So it's not necessary that it is like this. Yeah, so this could be made like this as well. You could have locators on both your plates, on the core side as well as the cavity side, and this will penetrate into the mold. And you generally, a rule of thumb is, you want to arrange them in a pattern. Like, this is the side view. On the left, I'm drawing the top view. So you want to arrange it in a pattern of a triangle or something like that, so that you don't have any chances of twisting or something like that, which rarely happens. But just in case, to prevent that, you can also arrange it in a triangular pattern, to understand in which orientation these things fit as well. So this is how you can prevent the mismatch, because they'll be properly designed to fit into each other. Yeah. Yeah, Arjun, you can unmute.
Sir, actually, I want to add one point also. Correct me if I'm wrong.
Yeah.
I saw die. They use four pins to join the core and cavity.
Yeah. So
Four
that's what.
different
So
pins.
see.
My question is, they
Yeah.
instead of making all the four pins same, they what they did was they makes three pins of same size and fourth pin is of different size.
Yeah.
So that is.
So okay, so this is what we designers call something as foolproofing. So foolproofing, in the right terms of, if you're going to take it literally, is making whatever you're designing, you got to make it foolproof. Matlab, if there is a fool, a person who has no brains, assembling your part, also shouldn't be able to assemble the part wrong. So by making three long and one short, what will it ensure is, if by chance, since you said four, so mostly four are at equidistant positions from each other. That's how we arrange it, so to prevent any angular distortion or something like that. So if someone were to arrange it in the wrong direction, let's assume a complete cube, right? Cube is same from all directions. If someone is trying to assemble it wrong, what will happen is, the longer part wouldn't go into the shorter part, as well as the shorter part will not fill the whole of the longer part, and there'll be maybe some shaking and something like that, and you'll understand that it is done wrong. So again, when I showed you now, this I'll just trace slightly away, but this is a part of design for assembly, or DFA. So as I told you, right, you can have it arranged like this, three, with which are equidistant angles from each other, right? Say 120, 120, 120. Now they are arranged at equidistant from each other. Rather than having everything at 120 degrees, the more cleverer form would be to have it something like this. So here you will have maybe 180, here you will have 90 and 90. So now this cannot be arranged, flipped. So this, the locator pin that's going into this can never go into this. However, the locator pin going into this one can go into this one, or can go into this one. So this is called as foolproofing. So that is another way of foolproofing your device. Yes. So coming back to this, coming back to the topic, and how can we eliminate flash, right? So the easiest thing would be to ensure that the clamping unit that you're using. So your clamping unit could be pneumatic, your clamping unit could be hydraulic, or your clamping unit could be a mechanical setup combined with hydraulic or pneumatic system. So in now, I do not have time to get into the entirety of the clamping unit, but while picking the part, or while picking the clamping unit, you need to ensure that the part stays closed at all given points of time, and it does not pop open at any point, no matter how much pressure is being applied on the other side. Secondly, if possible, if your part allows it, try and reduce the amount of pressure that the injection is applying inside the mold. If that is also not occurring, ensure that the air ducts that you have, the air vents that you have, is venting out correctly and it's not clogged or anything like that. Or maybe this is the last option, okay? Because if you tend to increase the venting hole diameter, so you will have plastic seeping into it, and that will cause surface deformities on the plastic as well. So the easiest thing to do would be to reduce the pressure and see if that is possible. Second easiest would be increase the clamping pressure. Third would be to check whether it is venting out correctly or not. And we have weld lines. So can someone tell me about what weld lines are? Like look at the figure, and if you could, because it's very similar to the flow line concept. Can someone tell me why does this occur? The only person talking over here is Arjun and Soumya in text. Guys, come on. And Vinay also said something about blue matching to be done. I did not understand that, Vinay. So guys, come on. Let's converse a bit here. Let's keep this little fun, because trust me, you guys will fall asleep and y'all will not take away anything from this. Arjun?
सर जब ये मोल्ड के साथ टच होता होगा ये पार्ट, आई थिंक तभी ये बन जाती है वहां पे एक लेयर, ये एक सरफेस डिफॉर्मेशन की टाइप ही हो गया.
सरफेस नहीं है एक्चुअली, इट्स थोड़ा यू आर देयर, यू आर वेरी क्लोज.
जहां पे वो कनेक्ट हो रहा है मोल्ड,
कनेक्शन पॉइंट. यस एग्जैक्टली. मोल्ड निकाल दो. कनेक्शन पॉइंट इज द कीवर्ड. व्हाट कैन यू थिंक अबाउट व्हाट कनेक्शन?
कोर एंड कैविटी कनेक्ट हो रहे हैं ना अभी.
नहीं कोर एंड कैविटी का नहीं है. ओके.
पार्टिंग लाइन
नहीं, पार्टिंग लाइन भी नहीं है. ओके, हु आस्क्ड me है? या भाई टेल मी.
Sir, for example, when we made like a hollow part, जब material inject करते हैं, और जब material core को surround करके जब opposite surface पे met होता है, that time sir ये weld line form होती है.
Exactly. Perfect one. Arjun, really good thinking on that one. Parting line, no. Soumya, parting line is not a defect. Parting line is necessary, and कुछ भी कर लो, parting line नहीं निकाल सकते. It has to be there in the component. Okay. Weld line is formed due to this. Okay. So as above, yeah. So कुछ लेना देना नहीं है. It is now, as you see, the gate is over here, right? So the plastic is going to flow आराम से खुशी आसपास. It's going to fill the mold up happily. But when it reaches this position, right? तब यहाँ पर आके एक डिलेमा हो जाता है प्लास्टिक को कि कहाँ जाना है, राइट जाना है. Now you have certain amount of plastic, molten plastic flowing over here, और ये इसने इसको कवर कर लिया. ठीक है, ये हो गया उसका one part of the surface of plastic. Now this has its own outer layer. फिर यहाँ से आएगा दूसरा पार्ट, और it will cover this one up like this, right? So now what has happened is there are two different layers of plastic.
तो सर वो मतलब सॉलिडिफाई होना शुरू हो जाएगा, तब तक वो उसका टेम्परेचर उतना नहीं रहेगा कि वो ज्वाइन हो सके होमोजेनिकली.
Exactly. So ये दो अलग layers जब भी form होते हैं, because the outermost, as I told you, ये real world है, so you will have cooling, right? So since this is the outermost layer, it will start solidifying, and the temperature, as just now Arjun pointed out, will not be enough to create a homogenized structure over here. So वो join तो हो जाएगा, चलो, it will stick, but it will yet have that line, because since it has cooled at different rates and it is coming close, that's why it is going to form this line. Now how do you prevent this? Okay, so who can answer इसको अभी prevent कैसे करना है? Arjun and Vaibhav.
To ensure the proper pressure, ताकि वो कूल होने से पहले वहां पे पहुंच जाए दोनों साइड से, चाहे जैसे मर्जी.
नहीं, that will not work when it comes to this. That is another.
तो फिर सर हम वो यूज कर सकते हैं कि वो मटेरियल हमारा वार्म रहे तब तक, जब तक वो पूरा मटेरियल फिल नहीं हो जाता.
Yes, that is one of the options. Not the best options, but one of the options. Vaibhav?
Sir, we can change the position of the gate.
Perfect. Where would you recommend I put the gate?
Sir, we can use diaphragm gate.
uh, Changing the gate won't work. Changing the position of the gate would work. Think about that. Changing the gate will not
Let
cause much of a difference.
let me think, sir.
Yeah,
Changing
sure.
the gate of position, sir.
Yeah, where should I position it?
We should place at the middle that that
So we
pouring
can provide
plastic
gate
should
below the product.
perform easily.
One person at a time. One person at a time. Let Pranay speak, Vaibhav. Yeah, Pranay.
Sir,
It's placed at the center, sir. That so that the flowability is easy to the corners at both the
Okay,
corners.
okay. That will come with its own problems because you will have your the connection point for your gate. So that will not be recommended for this particular. Only in this particular example, tell me. Okay. Yeah, Vaibhav, you were saying.
sir, like here in case we have provided the gate on the edge of the product, but we can also provide the gate on the bottom side.
बराबर. ठीक है. So now see, I'll tell you the problem that Pranay had said. Pranay and Vaibhav, right? Both of your answers are correct. Arjun's answer was the second option which we can go for. But again, productions भी ध्यान में रखना है. So I'll just explain what will happen with all of them. ठीक है? First we will go with Pranay's answer. So Pranay's answer was let's place the gate in the middle. शायद से नीचे से submarine gate या कुछ करके from down we'll try and inject it into the this cavity, right? But now when you start injecting it into the cavity, you will have really good flow. So chalo sub side se flow ho gaya. It is very close to the hole. It will stay at the right temperature and everything will be followed. But now if you pick up any component that is injection molded, you will notice something like this. ठीक है, एक बड़ा circle, एक छोटा circle, and उसके बीच में you will find one very ugly looking solid part. साइड व्यू में देखेंगे तो सॉलिड पार्ट में ऐसा थोड़ा सा एक ब्रेकिंग पॉइंट रहेगा, थोड़ा शार्प भी हो सकता है. नाउ दैट इज द पॉइंट वेयर योर गेट was connected to your plastic component where it was broken after the component was formed. This is something that is not avoidable. ये avoid नहीं कर सकते, parting line avoid नहीं कर सकते. No matter how hard you try, you can never avoid a parting line. Then let's come to Vaibhav's answer. So Vaibhav's answer was let's reposition the gate to this part. Okay. Now, if I put the gate over here, yahan se when the plastic starts flowing. Now, since the temperature is going to be really high at entry, abhi now since it traveled this distance, let's call this distance as x. Let's call this as 2x, for example. Now, this distance is barely 0.5x, no? As compared to this. So if you understand, itna distance travel karne ke baad, the plastic will start cooling at a much higher rate. So when you inject your material from here, you will have really warm material to go around and yet have the temperature ताकि ये point पे वो दो अलग surfaces form ना करे. It will not have two different surfaces and it will be properly molten. Then let's come to Arjun's answer, which was to keep the mold warm. Now, again, we keep the mold warm. It will work as a charm. It will form the best product, give you the best surface finish. But again, it will reduce production tremendously. So these were the two ways that you could change it. One is change the gate location. Second is by, keeping the mold warm. Both can be applied. Changing the gate location is much more preferred because you can keep the same rate of production. Always keep one thing in mind. You want to design something that has a really, really good rate of production. Agar rate of production kam hoga, the number of manufactured parts will be much lesser. Any kind of failure or say during assembly, if your part breaks, that would, the time of production also would get accounted over there. So that's why we need to ensure that parts are manufactured at a really great pace. Last, we come to sync marks. Now, sync marks, I'll just run through quickly. I'll give you guys like 30 seconds. If someone has something to tell me about sync marks, you can unmute and tell me about what do you know about sync marks. I'll just have a sip of water in the meantime. So I don't know how this flow pattern works. Can you explain again? Okay, just give me 1 second. Guys, drop your questions in the chat box. Don't go to accessibility and question and answers. It'll be much more tedious to for me to get there also. How the flow pattern works? Can you explain it again? Kiran, let me complete with the webinar. I'll get back to that. Okay. Don't leave before that. Yeah. Does anyone have any idea about sync marks?
Due to the shrinkage, I guess.
Okay, shrinkage is the right this. Different again over here. Uneven cooling is going to play a big role, and shrinkage also. Both of these will go hand in hand to cause these sync marks. Now, what are sync marks? Is this ugly kind of dimple like thing that you can see over here, over here. Now, these things occur because of uneven cooling, and I'll show you how. Now, okay, let us assume this is a cross section of a plastic part. Okay, so yeah. So if this is the cross section of a plastic part, say you added a you want this cylinder kind of thing over here. Okay, full solid cylinder. Now what will happen is when your 1 second, I guess I can draw it better. Yeah. Okay, this will be easier to understand. Okay, so now you will have plastic entering from here, flowing into this, okay, downwards and filling this up. After this fills up, it will come till the top, it will get completely full and plastic will continue flowing. Now इसमें problem क्या होगा is yeah. Now when your plastic comes in, right, it'll stick to this surface, then it will flow over here and it will come over here. So now let us break this thing into different layers. Okay, since it is filling up from here, we will consider layer 1, layer 2, layer 3, 4, 5, 6, 7, 8. ठीक है, आइडियली ये सारे लेयर्स 1 by 1, लाइक ये पहला कूल होगा, फिर ये सेकंड कूल होगा, फिर ये थर्ड, फोर्थ, फिफ्थ, सिक्स, सेवेंथ, एथ, नाइन्थ, ये ऐसा धीरे 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 करके these all layers should cool, right? But what happens is when these layers start cooling, right, the entire component that you have, so yes, so the entire this that you have, the lowermost layer, now the lowermost layer is going to cool evenly, for example. Second, what will happen is the second layer will cool at the core little better. The third layer also will cool at the core little better. So now these different layers start pulling the other layer towards it. And by the time you reach the top, this हमेशा core पे cool होके नीचे आ जाता है वो. So what will happen is by the time you reach here, you will have something like a small depression. Then this small depression grows even larger and even larger and even larger. So at the end of it, you are left with something like this. So now why does this happen? It's because we have left a lot of solid. We cannot have a lot of plastic ever in any concentrated point. So why do we add this cylinder or jo bhi parts अपन add करते हैं? Mostly it is because of design features. Now this is what we call as a rib, right? This rib provides thickness to your component. But if this rib is not designed properly, there's a particular way, there's a particular calculation where a rib is designed in a particular way. Like अगर ये lower part है, ये thickness है, ठीक है, यहाँ पर एक circle draw करते हैं, and there is a couple of calculations that you need to ensure that this circle touches the fillets that you are going to give to your rib. अभी वो थोड़ा ज़्यादा dense हो जाएगा, so I'll not cover it in this one. But yes, you need to perform a proper calculation. This rib thickness, इसका जो thickness है, it cannot be more than 40% of your material's wall thickness. Okay. The height of the rib cannot be more than 5 times the thickness. It cannot cross this. If it crosses this, you will have a sink mark forming. So now, how do you create these materials? Okay. Now, this is very similar to the drawing that I had made. This is what you want. Now, if we consider this lower surface, ये जो surface है, to be the aesthetic surface, so this is the shape that we want on the outside. कि ये जो एक shape है, ये हमको चाहिए. So rather than having a proper solid plastic component like this, where this entire thing is going to be full of plastic, what we can do is we can rather take this part and instead of having a straight wall below, since the upper part is the aesthetic component, we can go like this this and like this. So ये थोड़ा सा गलत किया. Just imagine this part and this part has the same thickness. Okay, so we can ensure that there is uniform wall thickness. Now if you see, if this we consider as 1 mm, ये throughout में पूरा 1 mm ही रहने वाला है. By having uniform wall thickness, we ensure proper amount of cooling, a good rate of cooling and an even rate of cooling. Second, we ensure that the component does not develop any kind of sink mark, because sink marks look bad. Okay, and they are like the first point of any kind of failure, similar to weld lines that I had shown you over here. These things, right? Any kind of surface defects. Now, for example, if this part were to be a load bearing part, where I put like the ye shape ka I put a part over here and I try to pull it in this direction. If this weld line is present, first ripping will start occurring at the weld line. ठीक है, ये ऐसा फट फट के the entire component will rip itself apart. So that is how we prevent it. ठीक है. So this is the defects that we need to keep in mind. Last one is short. So basically short ये होता है कि material कम पड़ गया. Simple words. So for example, if this is what we had to create, but and this needed say 500 grams of plastic. Of course, it will not need 500 grams. It's a very small piece. And this is, sorry, grams is not the right term. We will have to consider it as volume. So say cube of plastic in liquid form. We needed that much amount of plastic. But while calculation, हमने सिर्फ किया 350 cube. So क्या होता है is the material will end up being something like this. It will end up being short. The material that you inject will fall short. So how do you counter it? This is one of the very most simplest defects कि जितना डालना था उससे कम डाल दिया, उससे थोड़ा सा बढ़ा दो. Increase the maximum short that you are loading. If you have reached the maximum short in the machine that you have, you cannot do anything. Now this generally does not happen for one component, because one component is very easy to calculate. But दिक्कत तब होता है जब बहुत सारे components बनाना है. So when you're making, say, the spoon, right? The spoon is never going to be manufactured as a single spoon. It will always be made in pairs of say 16, 20, 50 sometimes, depending on the machines. So ये हो गया तुम्हारा main sprue, right? Now your sprue goes to connects into the main runner. Now this main runner connects to sub runners, right? These sub runners have different gates on them. यहाँ पर and ऐसे बहुत सारे gates होने वाले हैं इसके ऊपर. Now each gate is connected to one spoon. So say this is sub runner 1 के सारे spoons properly बन गए, sub runner 2 के सारे spoons properly बन गए. But जब आप sub runner 3 का देख रहे हो तो ये यहाँ पर जो spoon बनेगा ना, या फिर यहाँ पर जो बन रहा है, these spoons may fall short in material, because of course it will fill from the side that you are filling it in. So you need to do a proper mold flow analysis and understand the volume of material needed. In fact, many a times in industry, we will go for say 5 to 10% more. If you need 100 cube, we will go for 105. We'll go for 110. What will happen with excess material? If you have got a really good clamping system, you can get away with no defects or anything like that. But if you go with lesser material, that entire batch can be wasted, because for example, agar your mold flow is so even that sare points pe, your plastic is reaching at the same time at the tips, and then it falls short. All of your spoons will not have the head, basically. So this is what we need to take into consideration. Now, let's come to design for manufacture of plastics. I'll quickly fly through this. Any questions I'll answer after this, okay? Because we have reached 1 hour. So yeah, so basically you have your core and your cavity over here, and this is drafting. So as we had discussed in the previous lecture, I had taken drafting in detail. I'll just give it a go again. So this is the core side that you have. This is the cavity side that you have. And this is your plastic part, right? When your plastic part cools down, it will tend to shrink. Now, because of shrinkage, what happens? It starts sticking to the core side. Now, when it sticks to the core side, if your walls are parallel to each other, straight, you will have a very high amount of surface friction, which will be almost impossible to break. And when your ejector pins try and push this material out, it will form scratches on the material. And over a period of time, during after say 3 lakh 4 lakh cycles, your mold also will start wearing out, and then those scratches will become permanent features into your component, which of course you do not want if you are designing a really good component. So the easiest way to counter that is by giving a positive draft angle and making it little wide. Now, a fun experiment for you guys. Go home, like if you are sitting at home, go around, go to your kitchen, search for plastic components, plastic glasses. Then you can look at bowls. You can like anything like which will have side walls. You will notice you'll never have straight walls. It will always have an angle. So drafting is a not a it is the most important part of manufacture in plastics. You cannot get by without having plastic components having a draft. So for plastics we have a minimum draft angle of 0.5 degrees to 3 degrees. Okay, this is the golden rule. We have to have this. You can have it more than 5 degrees as well, 5, 10, 20 degrees also. That is like freedom, but this is the minimum requirement. If you do not have this, your plastic component will 110% fail. The other one is molding draft. That is when we use it for mold for aluminium or for casting, basically, not molding, casting draft. So that is for aluminium castings, for metal castings like iron casting and things like that. There also you need to ensure draft. So anywhere where you're going to be pumping liquid into a particular mold or a particular die, you have to ensure that it has a draft given to it so that it can separate easily. When you're talking about castings, iron castings, you can get away with having parallel surfaces, because if you are using something like a sand die for it made out of wet sand, so that can resist it. Okay, so after drafting we come to uniform wall thickness. So again, over here the only idea is, if you have this wall thickness that is so abrupt, that is, say if this is like 3 degrees 3 mm and this is 1 mm, what will happen is, because of this sudden reduction in the wall thickness, you will have some form of jetting occurring over here. So jetting or throttling, basically, because the cross sectional area is reduced, all of that pressure is going to be converted into velocity and jets of plastic will shoot out. And because of the jets of plastic shooting out, you will have a very varied pattern that will come on the outer surface, as well as you'll have very different very uneven cooling. Rather than that, what we prefer is having a very gradual change in the wall thickness, as well as ensuring that all of this is always filleted. So another fun fact or necessary thing, that while designing any component, in fact not only plastic components, any component that you plan on getting into the real world, until and unless a sharp edge is not specified or a sharp edge is not, written down that this is required, you never have a sharp edge on any component. You always want a component to be filleted. No matter what you are designing, having something like this is not going to work. You either have a fillet. If you cannot have a fillet, you want to have a chamfer. And in plastics, filleting is very critical, because pushing the plastic into the tiniest of corners is going to be very difficult. It's going to be impossible and cost a lot more money than what you can afford for. So always provide this fillet so that the material just rolls off that corner, rather than you forcing it into that corner. So that is one more important thing. And the last one is shelling out thick sections. So now, if this entire component is to be made of solid plastic, what will happen is, this portion that you see where I'm drawing with the pen, you will notice that this entire portion will sink down, and because of that sink, you'll have a circular sink mark in this. And this is guarantee, like there is no two ways to this. No matter what you do, even cooling, keep the mold heated, anything that you do, the sink mark will occur because of the sheer bulk of plastic. Second thing is, you will be wasting a lot of material in there. Rather than that, what you do is you shell it out. Now, what is the difference between this one and this one when it comes to strength? Of course, a solid component will be the strongest, But when you hollow it out, you can get almost 90% of the stiffness and the strength. But and the circles that I've drawn is basically you've hollowed it out, you've removed all that material. So you save up on this material. This saved up material can, I guess, make another component of the same dimension. So you're practically making two components in the price for one that you had originally designed. Second is when you are going to provide these ribs, they are more than enough to provide stiffness. So another thing that you want to keep in mind is always design your components so that they are stiff, but do not consume too much material, because the more material you consume, you will run into a loss eventually. So yes, this is the end of the presentation. Does anyone have any questions? If no, then I'll quickly take you through a few courses that we have in plastic design as well. And post that, I'll share the feedback form with which you can get your certificates.
Sir, can you elaborate something about the sliders we use?
Sliders for, okay, so you're talking about side cores and sliders. Arjun, just do me a favor, hang around after the entire session is over. So I'll take the slider part over there, because since it's not a part of DFM, it's a part of design itself. Just hang around a bit and I'll tell you about sliders and lifters as well. Okay.
Okay, sir. Okay.
Yeah. So yes, there was one question over here in the Q&A section. Yeah, that was by Kiran. He did not get how flow pattern works. So I guess, Kiran, you are talking about this, right? Yeah. So basically what happens is, I'll take you to the part itself. Yeah. So gate, right? Over here. So the flow pattern, basically, like if you follow these arrows, right? This is generally how the plastic will flow into your component. But what happens is after the plastic has traversed this entire duration, this entire distance, it starts cooling down. Okay. Not completely solid cool down, but of course you will lose like around 5 to 10 degrees. And the outermost surface. So now imagine it to be in the form of, if you have played with slime, okay, like I remember when I was small, that time we had this thing which will come in a bottle, like a slime kind of thing. So imagine your plastic to be slimy and flowing around inside the mold. So the outermost surface is going to be cooler. The outermost surface would be much closer to becoming a solid as compared to the inner core of it. Okay. So now I had explained this with a cylinder. So imagine this is the hole. This is basically the cylinder that your plastic cannot enter and it has to go around it. So when your plastic comes from here as a entire jet or whatever you want to call it, like a river kind of thing, now it has a dilemma. It cannot flow like this and then come around and meet over here, right? It'll come across this, it'll crash, it'll fill this portion up, then you will have plastic wrapping around. Now, when this plastic wraps around, you will have this loose plastic forming one layer. So this layer that you see over here is the outermost layer. Second, either say when the plastic will come in, here also you will have another outermost layer. So when these layers are not at the temperature that it was over here. So for example, if I were to, don't quote me on this, but let's consider this as 100 degrees Celsius. By the time it reaches, this entire wraparound thing and everything till it does that, you can say that this would be somewhere around 85 degrees Celsius. You'd have like a 15% drop in temperature. Now this temperature is not enough, and let's consider that your plastic will solidify at 40. For 40 भी नहीं, 50 consider करते हैं. 50 पे your plastic will solidify. So now this temperature over here is not enough for it to solidify, but it is not also hot enough for it to homogenize and mix over there and form a proper homogenized surface. So because of that, this outer surface, they will stick together. They will have certain amount of strength, but it will never ever form a homogeneous or uniform looking surface. And weld lines is actually the wrong word to represent this. It should be called as a weld plane. Okay. Because what happens is, if we consider this in the 3D space, and when an object will connect, say this was your cylinder, right, over here. If this was the cylinder over here, when it comes around the cylinder and when it touches over here, you would practically have a plane on which these 2 points are connecting. So I hope that has answered your question. If it has not, please put it in the chat box or unmute yourself. So yes, now I'll just quickly run you guys through ETG's website, where if you want to get into automobile design or you want to get into design engineering, it would be a really great place to start if you want to get into a really good company in the industry in the core domain. So you come to ETG's website. As you can see, we've partnered up with SAE India for these courses. So you come to internship and courses. You go down to engineering design. There you will find engineering design. Click on it. Okay. Now, when you scroll down, go to the third course, and this course is called as the specialization program. So this specialization program is basically an amalgamation of 6 major different courses. Okay, so here you will have different like 7 different courses, and all of these courses feedback. Thanks, DB Jen. Just wait till I finish this. I'll post your feedback link. So yes, yeah, the first course is automotive plastic design. Over here, you will learn how to design different parts on a car. That is front bumper. You will learn to design the interior dashboards, the center console, then different plastic trims that go inside the car. So you learn to design those projects where you will have to put in the research. You will have to work on these projects, and these projects can very well replace your final year projects on your resume because they are either equal or even better than some of the final year projects that people come up with. So then you have BIW fixture design. That's 20 lakh units manufactured. And that is why, guys, whoever asking for the feedback link, give me 2 minutes. I will finish this and then you will get your feedback link. Okay. And if you leave without filling the feedback link, you won't get the certificate. Structural analysis of BIW. Here you will basically be performing FEA on the body in white of your car. The body in white is basically the skeleton of your car. After you remove all the plastic parts, you remove the seats and stuff like that, you get the body in white. And this body in white basically defines how strong your vehicle is. So you'll be performing tests on it to see whether it's going to be crash worthy, whether it can sustain different types of load like cornering and braking and acceleration, and things like that as well. Then you go to automotive aerodynamics and thermal analysis. So what this is basically performing CFD on the vehicle, where you understand how aerodynamics affects the modern day cars, and you learn to design for optimal aerodynamics, and also for thermal analysis, where you understand how to take away heat from your vehicle into the engine bay and things like that. Along with this, you will also be getting a course on how to work with SolidWorks. So basically, over here, plastic design and sheet metal will be taught in CATIA. BIW fixture design will be taught with NXCAD, and sheet metal and the SolidWorks course will teach you how to design all of this using SolidWorks as well. So you will learn all the 3 major tools over here. Apart from that, you will be learning Ansys. You'll also be learning HyperWorks. So then last we come to race car vehicle dynamics, which is one of the most interesting modules, as you will learn how to build a proper race car right from scratch. Then if you come over here, you look at the different types of projects that are there. You have muscle car front bumper design. Then you have luxury car interior design, where I already spoke about a couple of these, right? Full frontal crash analysis, where you learn how vehicles crash and deform, and how you can prevent passengers from taking any kind of damage. Then you have Formula One front wing analysis. If you have ever wondered about why there are so many winglets, why are there so many canards on the front wing of a car, of a Formula One car, you'll understand that. Then you will learn to design an entire steering system in vehicle dynamics, as well as you learn to design ATV suspension. So when you come to the website, make sure to hit the ask an expert, where an expert will directly come in contact with you and explain to you how everything works. You can see the price of the course. It will keep on changing over here, and you'll get the best prices once you hit ask an expert. Also, since you guys have made it till here in the entire session, I'll be providing you with the feedback form. Along with that, I will be providing you with the link with a coupon code with which you can get a discount of minimum 20%, and it can scale up later on. So yes, you'll also be getting a discount. Yeah. So the feedback form has been posted. You'll also be getting. I'll also be dropping in the Elite Techno Groups website link over here, and along with that, the coupon code as well. Yeah. Okay, so I've posted the coupon code. The first link that you'll find is the feedback form. The second link that you will find is the ETG website, and the last one is the coupon code, which is active only for 24 hours. So go and get it before that. You can always hit ask an expert over there, which will help you out. Akshay, yes, you can leave. Fill the feedback form. If you do not fill the feedback form, you will not get your certificate. Arjun, yes. So your question was about lifters, right? Hello, Arjun. You can unmute.
Yes, sir. Sliders.
Sliders and